Hello everyone, my name is Sooryansh Asthana and today I am going to present before you our work on quantum communication with SU2 invariant separable states. This work has been done in collaboration with Rajni, Bala and Professor B. Ravishankar from IIT Delhi. This is the archive number of this work that we have posted. If one is interested, one can visit. First of all, I would like to begin with thanking the organizers for giving me this opportunity to present our work. This is the brief outline of the talk. That first of all, I would like to give the motivation behind this work and preliminaries that are required, and then I would go on to the central stuff, that is the transfer, how one can transfer information from a known qubit and an unknown qubit to a remote qubit, and then I would go on to show that the transfer of information can be done from a qubit to a remote qubit and swapping of quantum discord from two process level systems to a single 2s plus 1 cross 2s plus 1 level system. Now, the ubiquitous feature in all these protocols is that none of them imply entangled states. Everywhere, the states that are implied are separable and discordant. And then I would like to talk about the conclusion and future scope. So, motivation. So as we know that quantum entanglement is used as a resource in quantum communication, for example, quantum teleportation or supertransporting or remote state preparation. But at the same time, we know that it is very hard to prepare and sustain quantum entanglement because it is very fragile. Okay, so this has led to the study of quantum correlations beyond entanglement. For example, quantum discord, geometric discord, etc. So the point is that in all these quantum correlations beyond entanglement, the feature that is observed is that there is a sharp decline in the performance of the protocols in which discordant states are used. For example, in quantum teleportation, the teleportation fidelity drops down. Okay, so the question that we want to ask is that do there exist separable discordant states in 2 cross 2s plus 1 dimensional systems? Meaning, we are relaxing the condition that instead of transferring information from a qubit to qubit, if we can transfer information from qubit to qubit, with the restriction that the channel that we want to use is always a separable channel and it can have non-zero discord. So does that kind of a channel exist? And if that exists, what are the protocols that we can propose and what is the advantage that we can garner from that? So the starting point for us is that the information of a qubit is included in its block vector. Okay, if we know a block vector of a qubit, then we essentially know its axis of polarization and the magnitude of that block vector. Okay, so the information is included in the block vector. So if we want to transfer this information, the minimal requirement is that such discordant state should be SU2 cross SU2 invariant. This is required because this invariance will facilitate us to change the polarization of the remote qubit. And when I'm using the word polarization, I mean that the polarization in the spin operator basis. Though the protocols are not restricted to that basis we are using only for the sake of simplicity. Okay, so if the states are SU2 cross SU2 invariant, then the polarization of the remote qubit can be changed in a controlled manner by making some transformation on the qubit or by making some measurement. So as we will go along, I will make these points clear and rigorous. So such SU2 cross SU2 invariant states, interestingly, have been identified in this work by Bharat and Ravishankar. This is the reference, which is 890621110, and they have been termed as equivalent states of two qubit noisy entangled states. Now, here there is a jargon, entangled states. So first of all, we want to give meaning to what entanglement equivalent states mean. So for that, we first want to briefly summarize the definition of spin coherent states. So if n theta phi is a spin coherent state, then that n theta phi can be generated by these operations. Okay, that is the operation of SU2 on the stressed case. So that is SZ is equal plus S state. Now the set of all spin coherent states forms an over complete basis, and this facilitates us that we can expand any row in terms of its diagonal element, and this gives rise to Q representation. Q representation of a row of a state row is given like this: f of n is equal to 2s plus 1 over 4 pi. This 2s plus 1 over 4 pi is because we demand this Q representation to be normalized over a sphere. Okay, so equivalent state is two states belonging to two different Hilbert spaces are termed as equivalent if they share the same Q representation, meaning one state belongs to two-dimensional Hilbert space, the other state may belong to 20-dimensional Hilbert space, but if they share the same Q representation, then we will call those states as equivalent states. So the example of these states is, as we are all familiar, the single qubit state can be written as half 1 plus sigma dot p. The equivalent spin S state is written as 1 over 2s plus 1 identity plus s hat dot p hat. Okay, this is because both of them have the same Q representation. So what will be that Q representation? That will be 1 plus and hat dot p, and with a factor of 4 pi. Now, in order, what is the property of these equivalent states? The property of these equivalent states is that if we use the so-called equivalent observables, which I will explain in a minute, the equivalent states yield the same expectation value for all the observable after suitable rescaling. For example, as we know that the expectation value of sigma dot n in the qubit state row is given by p dot n. But if we take an equivalent observable that is given by O prime 3s over s plus 1 times s hat dot n hat, where s hat is the vector is divided by s, then the trace of this O prime with the state row s is the same as p dot n. So as you can see that both these states give the same expectation value p dot n with some suitable rescaling of the observables. Okay, so this is just some definition. Now, what is the use of this definition? So the feature that emerges out of this concept of equivalent state is classical simulation of entangled state. So what is this thing? That if we take two qubit entangled one state, that is 1 over 4 1 minus alpha sigma 1 dot sigma 2, and everyone knows that the range of alpha is from -1 over 3 to 1. Now, the equivalent half cross S state will look something like this, as written. Sorry for this typo. This should have been 1 over 2 2s plus 1 identity minus alpha sigma 1 dot s2 hat. Now, this state is separable when mod alpha is less than or equal to s over s plus 1. So the point is that in the range where the two qubit Werner state is entangled, its equivalent that is sitting in higher dimension is separable. So for a given value of alpha, the minimum s for which row half cross S is separable is given by the minimum half integer or integer which is greater than mod alpha over 1 minus mod alpha. Okay. Now the thing is, as one can see, that suppose alpha is equal to 0.9. So 0.9 divided by 1 minus 0.9. So S is equal to 9. So if we take S is equal to 9 or greater than 9, then the equivalent states will be separable. If we take alpha is equal to 0.95, then the equivalent states with S is equal to 19 and higher, they will be separable. So the point is that how we can use this feature. That is the question that we want to address. And the first protocol that exploits this feature that we have proposed is transfer of information from a known qubit to a remote qubit. Okay, so as I have told you earlier, that all these protocols use separable quantum states as quantum channel. So the quantum channel as is shown here, it is 1 over 2 2s plus 1 1 minus alpha sigma 1 hat dot s2. Now if Alice wants to prepare an equivalent state of sigma 1 dot m, then what Alice does, Alice measures sigma 1 dot m on her qubit, and if she gets plus 1, then she asks Bob to do no information, and if she gets -1, then she asks Bob to do a rotation so that S2 dot M maps to minus S2 dot M hat. Okay, so this information is sent on a classical chain. Okay, so the point is that Bob does not have a qubit, but Bob has an equivalent qubit. Okay, and since Alice knows what her qubit is or what the measurement is that she has performed, she can send information about her measurement so that Bob, with suitable rescaling of observable, as I shown earlier, can retrieve the information from this qubit. Okay, so for example, if Bob wants to retrieve the information, then Bob has to measure an observable like 3s over s plus 1 sub s2 dot n hat, so that the same function, same expectation value gets he extracts the same expectation value. Now this factor of alpha is there. This is peculiar. So as you have seen that this equivalent states and this minimum value of alpha that one can have is given by this s over s plus 1. Okay, so the point is that for a given value of alpha, there is an s minimum, and for alpha is equal to 1, that s minimum is infinity. So one cannot transmit a perfect state. There will be some non-zero value of alpha, but since that quantum channel is known, Alice and Bob both, they can account for that factor also, so that they can retrieve that information. Now, after that, the next protocol that I'm going to talk about is transfer of information from an unknown qubit to a remote qubit. So let us say that Alice has an unknown qubit half 1 plus sigma 1 dot p, and she wants to transfer its information to Bob. Okay, so this is exactly like teleportation. The only difference is that the quantum channel is half cross S. Okay, and then Alice makes a measurement in the so-called Bell basis, and then depending on her outcomes, if she gets row 1, if that is the singlet state or the three triplet states, then she asks Bob to perform an identity transformation or a rotation about x-axis by an angle pi, or a rotation about y-axis by an angle pi, or a rotation about z-axis by an angle pi, so that Bob in all these scenarios gets 1 over 2s plus 1 plus alpha s3 dot p hat, and Bob, with using those equivalent observable, can retrieve all the information that is encoded in this state. Okay, so that is the thing, that here also the quantum channel that is used is separable. Now after this thing, the next protocol that we are going to talk about is transfer of information from a qubit to a remote qubit. So for that, let us say we have a qubit 1 over 2s plus 1 plus s1 hat dot p hat, and the quantum channel is the same as the previous protocol. Now Alice performs a measurement of this observable s1 hat dot sigma 2, and if she gets plus 1, she knows that the state that is with Bob is this 1 over 2s plus 1 minus alpha by 3 s3 dot p hat, and if she gets minus s plus 1 over s, she knows that the state that is with Bob. Of course she does not know the value of p, because the qubit is unknown to her. But the point is that she knows that in one of the cases the axis of polarization is flipped, in the other case it is the same. So that information she transmits to Bob, and by using that information, Bob can use the equivalent observable. In one of the cases, Bob will have to invert the expectation values, and in the first case, in which he gets 1 over 2s plus 1 minus alpha by 3 s3 dot p hat. In the other case, he does not have to invert the expectation values. Okay, so in this way, and here you might notice there is a factor of 3 sitting in the denominator. So that factor of 3, since it is a known factor of 3, so if Bob wants to if Bob wants to account for this factor, he can also account for this factor. So he can also multiply all the expectation values by 3, so that all the things that Alice has with that unknown qubit, Bob can also mimic those things. Okay. Now the last protocol that I'm going to talk about is swapping of quantum discord from two process level systems to a single 2s+1 cross 2s+1 system. So let us say that there are four parties: Alice, Bob, Charlie, and David. And Alice and Bob share this noisy equivalent of one state, and Charlie and Bob share this another noisy equivalent of one state. Now, if Alice and David perform a Bell measurement on the first and fourth party, the state that is left with Bob and Charlie is 1 over 2s+1 squared 1 minus alpha beta s2 hat dot s3 hat, which has a non-zero discord for every non-zero value of alpha and beta. Okay, so the point is that earlier Bob and Charlie were sharing an uncorrelated state, whereas at the end of the protocol, the state that is with them is having a non-zero discord. So the point is that in all these protocols, separable states have been used. I have not gone into the details of the values of S2 and S3 that if one is interested, I can discuss, and all those things are there in the preframe. So we can discuss those things as well. So the conclusion is that with the concept of equivalent states and classical simulation of entangled state, one can devise many quantum communication protocols, as we have discussed. And since all these states are highly mixed for higher values of S close to 20, then the quantum information, this implies that the quantum information processing can be done with highly mixed states, and for transferring information that is encoded in qubits and higher dimensional systems, one can propose the protocols by employing equivalent states of two qubit entangled states that will constitute a future area of study. And since nowadays multi-path experiment and orbital angular momentum experiments, all of them give with all of them it is realizable to have a higher dimensional quantum state. So one can essentially, we hope that these experiments can also be performed. Now we want to acknowledge Swami Kadikari for the questions and UGC and CSIR for funding. And thank you very much for your attention. If there are any questions, we can have those questions in Zoom meeting, and you can send me an email on this email. Thank you very much.